This video looks at examples 2 and 3 of your parametric equations day 2 notes. These are some projectile motion examples. So the first one says that Kyla throws a baseball with an initial speed of 145 feet per second at an angle 60 degrees to the horizontal. The ball leaves Kyla's hand at a height of 5 feet. Okay, so we have that Kyla is holding the baseball at 5 feet off the ground, right? And she's going to throw this. It's going to go up and come back down. At some point, it will hit the ground, okay? So some information that we need to kind of understand is that the angle at which this is happening, so the angle of theta from the horizontal is 60 degrees, and the initial velocity, the initial speed that this is leaving her hand is at 145 feet per second, okay? And so as a reminder, we can talk about the vertical height of this baseball, right? That's our y of t equation. And we can also talk about the horizontal distance of the baseball. That would be our x of t equation. So it's kind of just a visual of what's going on. So let's back up and look at the questions associated with this. We're asked in part A to find the parametric equations that model the position of the ball as a function of time. Okay, so we're going to utilize those functions from our notes above. Right, we have the the equation that measures our horizontal distance as being x equals our initial velocity times cosine of theta times t, and then we have our other parametric equation describing our vertical distance of our object, or in this case this baseball, being negative 16 t squared plus velocity initial sine of theta, all of that times t, plus our initial height. Okay, so we actually have all of this information. So you can go ahead and plug in the appropriate information. We know that x is then going to be equal to our initial velocity, which is 145, times cosine of our angle of projection, which was 60, and then we have our variable t. This can be simplified to x equals 145 times, we'll remind ourselves that cosine of 60 is really just 1/2. So we'll divide 145 by 2 to find that x is equal to 72.5 t. Okay, so that's the linear equation describing our horizontal distance. Okay. Now over here in y, we'll go ahead and plug in similar information. We find that y equals negative 16t squared plus 145 sine of 60t, and then we have to add our initial height, which is plus 5. Okay, again, this will simplify because we know that sine of 60 degrees is just root 3 over 2. So we can go ahead and say that this parametric equation is y equals negative 16 t squared plus 145 root 3 over 2 t plus 5. Okay, so we've now come up with our parametric equation that's describing our vertical height of the baseball. Okay, B asks how long is the ball in the air? Okay, so what we want to do is we want to figure out for how long was the ball following this projection, and at what value of t did it land on the ground? Okay, so we want to look at when is our height 0. Okay, so we want to take our vertical equation, the vertical distance equation, our y equals, right, this guy right here, our y equals negative 16 t squared plus 145 root 3 over 2 t plus 5, and we want to set that equal to 0. Okay, so the setup of our equation is going to be just that. We'll look at trying to find the t values that will make negative 16 t squared plus 145 root 3 over 2 t plus 5 equal to 0. And I notice that I have a quadratic equation, right? So the temptation is always there to subtract the 5 over, but then notice we're left with 2 terms of t on this side, and so that wasn't super helpful in this process of trying to isolate t. So we want to think back to our strategies for solving quadratics. We should always try to factor, but looking at this crazy equation, I don't really want to try to figure out, and I don't know that we can, what multiplies to negative 16 here, right? And multiplies to 5 at the end and then adds to give us this crazy constant in the center. So factoring doesn't look super appealing here. So I'm actually going to go ahead and use the quadratic formula. So reminder that our quadratic formula is, this will give us the x values, or in this case, I could say t values, right? That show when our function is 0, when our height is 0, and that is found by taking the opposite of your b plus or minus the square root of b squared minus 4ac all over 2a. And a little reminder that our quadratic is set up as at squared plus bt plus c. So we need to fill in our b, a, and c values here. So to figure out when our ball hits the ground, we're going to need to take negative 145 root 3 over 2 plus or minus the square root of b squared, so 145 root 3 over 2 squared minus 4 times a, which a in this case was negative 16, times c, which is 5. And then we need to divide all of that by 2 times a, which was negative 16. So again, we're just taking our values from our quadratic and we're plugging it into our equation, where negative 16 is filling the a's. We have 145 square root of 3 divided by 2 filling the b value. And then lastly, we just have the single c of 5 here at the end of our square root. So this is something that we definitely need to grab a calculator to continue. And remember, there's 2 answers, right? We have this plus or minus, so we're going to have to type in this numerator twice, right? We're going to have to do this calculation 2 different times. So we'll do negative 145 root 3 over 2 plus this quantity divided by negative 32. And then we'll do this again, negative 145 root 3 over 2, and then minus this quantity divided by negative 32. Doing that gives us the 2 time values of negative 0.034 and 7.888. Now, think about what time what t represents, right? T represents time. So this right here, this t value of negative doesn't really make sense, right? We don't know what negative time means, okay? So we're able to rule that answer out and identify that the ball was in the air for 7.888 seconds. In general rule of thumb, it's good to use 3 decimal places, and you see that reflected here. Okay, part C asks, when is the ball at its maximum height? Okay, so we want to know when, so at what t value is it up here? Is it up at the maximum height, at its vertex? Okay, and then we also want to know what determine the maximum height of the ball. So that would be y of t, right? We want to know the height as well as when it's occurring. Okay, so we saw in our notes that to figure out the t value at which our vertex is occurring, we can go ahead and use the equation negative b over 2a. And from our equation above, we know that b is 145 root 3 over 2, but we need that to be negative. And then we will divide that by 2 times a, which is negative 16. So again, we're just picking off these values from our equation above, our vertical distance equation, right? Our parametric equation for y. Okay, so this will give us that the vertex is happening at about 3.924 seconds. Okay, so that's when we hit the highest point. Now we need to know what is the highest point. So we're going to go ahead and take that value of time and plug it in to our vertical distance equation. So we'll have y equals negative 16 times 3.924 squared plus 145 root 3 over 2 times 3.924 and then plus 5. And this tells us that the maximum height of the baseball that was thrown is 251.387 feet. Okay, so what we've done here is we've calculated the vertex of that parabola that I drew up here that describes the shape or the path that our baseball took, right? So the vertex here is 3.924, 251.387, and that's representing when we hit the maximum height and what the maximum height was. Okay, last part of question 3 is we want to determine the horizontal distance the ball travels. Okay, so this one is set up pretty nicely. It tells us directly that we need to use our horizontal distance equation. Our horizontal distance equation is 72.5 t. And now we need to think about, well, what t value are we going to use? Remember that the ball was in the air for 7.888 seconds. Okay, so if we look back at our drawing, if we're trying to figure out the horizontal distance that our ball traveled, right? So this distance here, we're going to go ahead and utilize the fact that t equals 7.888 when the ball hit the ground. Okay, so we need to plug in 7.888 into our horizontal distance equation. So we'll find that x equals 72.5 times 7.888, which is equal to 571.880 feet. So what this means is that when the ball landed again, it landed 571 feet away from where it was initially thrown. All right, so one last example for this section of notes. We're looking at a pumpkin being tossed. This pumpkin was launched with an initial speed of 125 feet per second. So we have 125 feet per second representing our initial velocity. We have at an angle of 45 degrees to the horizontal, so that's our theta. And it was launched from an initial height, it looks like a catapult was used, of 25 feet. Okay? So we're asked to find the parametric equations that model the position of the pumpkin as a function of time. So just like we did before, we're going to be filling in our x equals velocity initial cosine of our angle of projection times t, as well as our negative 16t squared plus initial velocity sine of our angle times t plus our initial height. Okay, so plugging in all of that information, we find one parametric equation is x equals 125 cosine of 45 times t, which can be simplified to x equals 62.5 root 2 times t. That's coming from cosine of 45 being root 2 over 2. Okay, so dividing 2 into 125 and then multiplying by root 2. Okay, so here is our horizontal equation, and then we can go ahead and similarly calculate our vertical equation. So negative 16t squared plus 125 sine of 45 plus that initial height of 25. And we know that sine of 45 is also root 2 over 2, so we can simplify this and call it negative 16t squared plus 62.5 square root of 2t plus 25. Okay, so we've taken all of our initial information, right, our given information, our initial velocity, our angle of projection, and initial height to find the parametric equations that model the position of the pumpkin as a function of time. Okay, and question B just asks, how far did the winning pumpkin travel? And so we want to know, again, we have to kind of think about what's happening here, right? We have that our pumpkin got launched and landed on the ground. Remember, this is happening at a height of 25 feet. And so our pumpkin launches and it lands at the ground over here. When we're asked for how far did the winning pumpkin travel, what we're trying to figure out is how far away is it from the start, right? So what is that horizontal distance? Okay, so this question translates to, what is x of t when y of t equals 0, right? What is that horizontal distance once my y of t function has returned to 0, has hit 0? Okay, so we need to figure out what that t value is initially, first off. Okay, so we need to figure out what does this t value equal so that we can then plug it in to our equation. So again, figuring out what t value we have, how long did it take for our pumpkin to hit the ground, okay? So we'll take our vertical equation to start, our negative 16t squared plus 62.5 root 2t plus 25, and we'll set that equal to 0. Just like above, the quadratic formula is going to be your best bet here. I'm not going to write out the details. I think that's something that you guys can handle at this point. But keep in mind, you'll have two answers and we're going to need to figure out which one to use. So using the quadratic formula, we find that t is equal to negative 0.2697 as well as t is equal to 5.794. We've talked about how that negative time value doesn't quite make sense. So we're safe to grab that t is equal to 5.794. And maybe it's not the best idea to box that, right? Because that's not my final answer. The question wasn't when did the pumpkin hit the ground? It said how far did the winning pumpkin travel? So what we've done is we've figured out this t value over here. So now we need to take our horizontal equation, our x equals 62.5 root 2, and we need to plug in that time value. So we'll find that the horizontal distance that was traveled by our pumpkin is equal to 62.5 root 2 times 5.794. And grabbing a calculator, that gives us 512.122 feet. Okay, so again, what we've done is we've figured out how far away the pumpkin has landed from its starting point. And we had to first find the t value at which it landed on the ground.